So I usually wait until the room is silent. It must be time to start. So thanks for coming. Enjoy your lunch. This is Project Delta B, or Group Delta B, not Delta 5, Delta B. And they're designed an Afterburner, which they're going to talk about.
Hello there, we are Delta B Propulsion, and we designed a multiple configuration Afterburner. So our team members include myself, Catherine Higgins. I'm the DTL. I'm also in charge of the solids and design and safety groups. Troy Fenner, in charge of air breathing and advanced propulsion and CADS group. Karina Lyon, in charge of the LabVIEW budgeting groups. Matthew Siegel, in charge of prototyping and testing group. And Justin White, in charge of heat transfer and instrumentation. So, a bit of background, what is an afterburner? Afterburners typically provide around 50% additional thrust with a massive reduction in fuel efficiency for jet engines. This is a picture of our CAD model right now. As you can see, it goes from a 3.5-inch diameter inlet all the way 52 inches long to an 8x8 square. The model that I am passing around right now is a 1/3 scale model. So the need for this project. We hope to find a relationship between the positions of flame holders and blockage ratio, drag, and flame stability. We also want this to be able to be used as a teaching tool in the future so that future students can actually see how an afterburner works, get their hands dirty, see what's happening, instead of just reading about it in a textbook. We also hope that it can be used for future research so that students can go in, change things around as they see fit, and see how their questions can be answered. So our requirements. We decided that we needed a variable speed air source so that we could test at a number of velocities and mass flows. So we decided to go with a Toro PowerJet F700 electric blower. We also needed a variable fuel source, so we decided to go with propane because it's inexpensive and readily available. We also need to be able to measure temperature, pressure, and velocity so that we can find the relationships between drag, flame stability, and blockage ratio. So we are deciding to use thermocouples, pressure transducers, pitot tubes, and then LabVIEW to collect all of this data for us. We also want variable geometry so that other students can see how things, by moving the V-gutters and flame holders around, can affect how the results work. By the end of the year, so in May, we are going to have a working afterburner, an operation safety manual, a drawing package in CATIA of the entire assembly, LabVIEW code so that data can be collected, and analysis on the effects of blockage ratio, drag, blowout time, and flame stability. I will now pass it off to Troy Fenner to talk about design theory.
So I'll be going over the design theory of our afterburner. So currently we have 2 tests that we will be running. The first test right here, test 1 with configuration 1. This is what we're using to do all of our calculations and any sort of CAD modeling. Then, when we move on to configuration 2 during the testing phase, this is what we'll be using to test the effects of flame holder positioning on drag coefficient and blockage ratio. So our 3 predictions that we have going forward into testing is that when we move from configuration 1 to configuration 2, the blockage ratio and the drag coefficient will decrease while blowout conditions will remain the same. We believe this will happen because when we move from configuration 1 to configuration 2, the distance between these will become greater, allowing for more air to pass between the two, allowing for a decrease in drag and blockage ratio. Since the blowout conditions are met due to chemistry as well as geometry of the flame holders, we believe that altering the 2 configurations will not affect the conditions for blowout. So our blockage ratio. Our current blockage ratio with our geometry is 0.375. We found that using the equation on the screen. The recommended range for these blockage ratios of an afterburner is between 0.21 and 0.417. So with our current geometry, our blockage ratio falls within that recommended range. I'll be talking more about why the blockage ratio is so important because it affects a lot of the exit conditions of our afterburner. Now our drag coefficient. Our drag coefficient is currently 1.95. Now drag coefficient affects the total pressure within the system, which then affects the density of the air and ultimately affects the exit velocity. This is also affected by the geometry, so as blockage ratio changes, so will the drag coefficient. Now for our blowout conditions. Currently, with the current design, our stay time is greater than our blowout time. Now this is important because the blowout time for an afterburner is the required time it takes for the fuel to mix with the air, go through the chemical process necessary, and then ignite. So once that happens, you'll be able to have a stable flame. The stay time is the required time for the air to circulate and create that recirculation zone. So for our afterburner with our current design, the fuel will have enough time to mix with the air and then ignite and create a flame front right here. Now, as I talked about, the blockage ratio affects a lot of things within your afterburner. So, as we're looking at moving from configuration 1 to configuration 2, we see that the blockage ratio will decrease. That's what we're predicting. So if you decrease the blockage ratio, you should get a decrease in drag coefficient and a decrease of your internal velocities. Now, if you get a decrease of your internal velocities, your stay time and your blowout times will become closer and closer, which means you're moving towards a point where you will either get flame blowout or you will not even be able to ignite the flame. Now, on the other hand, if you decrease the drag coefficient, then you should get a decrease in exit pressure, which then will move on to a decrease in air density and ultimately an increase in exit velocity, which is what you want. So this equation right here shows you that as the density at station 3 decreases, we're looking at getting an increase of our exit velocity. And that's why decreasing the blockage ratio has such a great effect. Now, we found for our current design that our ideal range for testing is between a blockage ratio of 0.315 and 0.375. Now, as you can see indicated by the orange arrow, the current design value of 3.75 is where we're starting off with our current geometry. So if you move from right to left, that is a decrease in blockage ratio, which indicates as you decrease the blockage ratio, your velocity upon the exit will increase. Now, if we start at this point with our current design and we increase the blockage ratio, it is not effective for our testing because it'll just decrease the velocity. So we want to move from right to left. But once we pass this point of 0.315 for our blockage ratio, we will begin to get flame blowout. So the current calculations show that there will be an increase in velocity. However, we will get flame blowout, so that's why we must stay within this range. So an example of this is if you were to take the blockage ratio from 0.375 and move it to 0.325 while keeping the inlet velocity, the mass flow rate of air upon the inlet, and the mass flow rate of fuel the same, you will get a decrease, or an increase in your exit velocity from 700 to 716 inches per second, and decrease in your exit pressure, and the temperature will remain the same because the temperature is not affected by these parameters. Now, for keeping our initial condition of 0.375 for the blockage ratio and the drag coefficient, all the geometry the same, this is what we're looking at getting for our conditions within the heat chamber upon the exit. So our current maximum exit temperature is 1,351 Rankine, while our minimum temperature is 618 degrees Rankine. Now, to get the highest temperature in your heat chamber, you would have to put the lowest amount of inlet velocity with the most amount of fuel. This will allow for the greatest mixing and the greatest exit temperatures. Now, on the other hand, if you would like to get the least amount of temperature in your heat chamber, you would put the max amount of inlet velocity out of your blower and the least amount of fuel. This is important because it shows our team what ranges we have to design for in the future and what we're expected to get depending on what type of test we're running. So for the velocity within the heat chamber, our max velocity upon the exit is we are looking at 982 inches per second with a minimum velocity of 332 inches per second. As you can see upon this graph, the greatest exit velocity is with the highest inlet velocity and the most amount of fuel. That gives you the biggest bang for your buck. So that's this formula right here in this graph will show us with our current blockage ratio what we're expected to give. This is important because once we move on to the testing phase, once we start changing blockage ratio and drag coefficient, we'll be able to compare from what we're expected to get with our current design of 3.75 for blockage ratio to what we're actually getting during the testing phase. Now for the pressures. These are the average exit velocities, average exit pressures, and the change in pressures. This is because as we were running theoretical tests through Excel and calculations, we found that as we altered velocities upon the inlet and fuel ratios, we still maintained about the same pressures upon the exit. So right now our average exit pressure is looking at 13.19 psi with a change in pressure of 0.75 psi across the whole system. This is with an assumed initial pressure of 12.45 for the system. I'll now pass it off to Justin White for the design of the Afterburner.
For our current Afterburner design, we've sectioned it off into 4 main components. Starting with the entrance of the flow, we have the inlet labeled in blue, followed by the window section in tan, followed by the flame holder assembly in pink, and ending with the flame heat chamber in red. Starting with our inlets, the geometry in which we've chosen is to go from a 3.5-inch circle, which is the exit of the chosen blower, to an 8-inch square for the rest of the Afterburner over a course of 29 inches. This length is determined by the 9.22 degree diffusion angle in which we've decided upon. This angle was found using a fluids textbook that was recommended to us by Dr. Haven. And in this chart, you can see a diffusion angle comparative to the losses registered for that and marked on the graph by the red line. You can find that the lowest amount of losses is associated to a 9.2 degree diffusion angle. This will not help us reduce the wall shear stress at all, but it will help promote laminar flow as well as help prevent kinetic losses throughout this. While this does affect our total length of our inlet, we have chosen to compensate that by choosing a cheaper material for this. For our inlet design, we've chosen to 3D print it in 3 separate sections in the Rapid Prototyping Lab here on campus out of ASA plastic. These pieces will be printed using the ASA plastic and then glued together using the cyanidic glue. The printers in which we've chosen to use to print these, it will have a 0.005-inch layer height, which is the layer in which the 3D printer scans over and adds per layer. This will help us give a smooth surface finish that we can then sand down further. The smooth surface finish will then help us promote laminar flow throughout this piece. The reason we've chosen ASA plastic throughout this, number one, is so that it will help reduce costs as well as it can accurately create the geometry for this section due to the 3.5-inch circle to the 8-inch square and the angles that are attributed to this. In addition to this, this will also allow this piece to be considered swappable and replaceable for future tests. That way future groups and people that are using it to test different theories are able to use their own flow generators or different flow generators available in the Propulsion laboratory. Moving down the Afterburner, we next have the window section. The geometry attached to this is that it will be a total of 5 inches long with the 8x8-inch square cross section. The window inside of this section will be 3 by 3 inches with a 0.13-inch thickness to it. The material, the justification behind this section is mainly for safety and so that you can look at the internals of the flame of the Afterburner itself. Looking inside of it will allow us to tell and confirm the ignition of the recirculation zone, the blowout of the recirculation zone, as well as to have access for videos for future lessons and teaching. This position will also be considered a more permanent fixture inside of it, allowing it to hold instrumentation, including our fuel injector into the Afterburner. The material in which we're using for the window itself, we will be using a borosilicate glass. This was chosen based on several properties. Number one is its softening temperature and melting temperature. Its softening temperature is the temperature in which it starts to buckle or deform under larger pressures. This is 1,960 degrees Rankine, which is above what our current testing temperatures are. This is also not a temperature in which we need to worry about that much due to the low pressures throughout our system, but it is a temperature that future testing or teams might need to worry about. The next characteristic in which we've used to determine this material is it does not fog or become murky when exposed to combustion particulates, as well as it has a high oxidation and corrosion resistance attached to it. The last characteristic in which we used to determine this material was the coefficient of thermal expansion, which is 2.22 times 10 to the negative 6 inch per inch Fahrenheit. The reason this is the material property in which we need to watch is due to how much it expands when exposed to temperature, and this is a different coefficient of thermal expansion than what is used for the rest of this section. So we will need to use a seal between this and the rest of the window section to maintain safety for it. The material for the seal has not been determined at this point in time. The rest of the window section will be made out of 3/16 stainless steel sheet metal that will be 1/16 of an inch thick. This was chosen off of several characteristics. Number one, the service temperature, or the maximum temperature in which the manufacturer recommends it's exposed to under extended time period, is 1,841 degrees Rankine, which is much higher than our current testing temperatures. The coefficient of thermal expansion attached to this piece is approximately 8.89 times 10 to the negative 6 inch per inch Fahrenheit, which is approximately 4 times that of the borosilicate glass. Other reasons that we decided to use this material would be that it was inexpensive, as well whenever buying in bulk, as well as it is something that is easy to manufacture and mold into the shape we desire, or using the materials and the tools located on campus and the AXPAT. Following this section, we have the flame holder assembly, which the geometry attached to this is it will be an 8-inch section, and with the 8-inch by 8-inch cross section. Inside of this, it has two 3x6-inch slots cut out of the walls, as well as a 3x3-inch cap attached to each of these. The reasoning for this is those slots will allow us to move the flame holders throughout the flame holder assembly to different horizontal locations, allowing us to test it and compare the tests between each other. The slots will allow for easy positioning and moving, while the caps will allow to prevent loss of flow and anything else through that area. The caps and the flame holders themselves will help be secured, as well as seal that area using HVAC. The material we're using for this section, as well as the 3/16 stainless steel, this is to help reduce cost, so we can buy it in bulk, as well as to maintain conditions throughout it. The flame holders themselves will have a 30-degree angle inside of them and a mouth height of 1.5 inches. Their total length will be 8 inches. That way it can span from one wall to another of the afterburner, as well as be ended with a 3x3-inch plate that will go into the slots on each wall. The reasoning behind these geometries is that 30-degree angle is what we have found through research, as well as through our calculations, to have the best option of creating a recirculation zone, as well as it spanning across the entire length of our afterburner helps minimize or completely negate the possibility of edge vortices causing disturbances. As with the other pieces, this also will be made of the stainless steel 3/16 steel, which will help us reduce costs because we can use the pieces cut from forming the other geometries to create these, and possibly create other test pieces if we have time to perform more tests at different angles. The ending of our afterburner is going to be the heat chamber, which its geometry is going to be 10 inches long with an 8x8-inch cross section. The reasoning behind this is so that it can completely contain the expected theoretical recirculation zone caused by each of the flame holder positioning. It will contain the more permanent instrumentation at the exit to measure our exit conditions, so we can compare those conditions against the other tests, as well as the theoretical values, as well as it will be long enough to help dissipate a little bit of the heat that will be accumulating throughout the afterburner. As with the other pieces, this will also be made with a stainless steel 3/16 sheet metal, just to help keep down on cost and keep everything to where it moves together. I'm going to pass it off to Matthew Siegel for prototyping and testing.
So during the first semester, we completed computational fluid dynamics analysis using the ANSYS Workbench program. These analyses simulated our water and non-fire tests that we will complete next semester, and gave us theoretical results based on our flame holder design. Next semester, we will be performing 3 different types of tests: water tunnel tests, non-fire tests, and live fire tests. The main goal of our water tunnel tests is to confirm that our flame holder design creates recirculation zones. Recirculation zones are important for our afterburner because without them, during the live fire tests, the afterburner will not maintain a flame during the tests and will not function properly without these recirculation zones. Next, we will complete non-fire tests. The goal of these tests will be to obtain measurements that show how position of the flame holders affects the force due to drag along the outer faces of our flame holder design. The final tests type of tests that we will perform next semester are our live fire tests of our fully assembled afterburner system. These tests will help us determine how the position of our flame holders affects the blockage ratio and the flame stability of our afterburner. All right, so before we started any of our CFD analyses this semester, we completed Reynolds number calculations to determine the testing velocities we would use during our water tunnel tests. The first step that we took was to determine velocities that we would use for our non-fire and live fire tests based on the capabilities of our blower that we are using. These velocities are shown in this column here. Then our air breathing and propulsion team completed calculations to determine the velocity at the flame holder assembly inlet, which would be affecting our flame holders themselves. These velocities are shown here. Those velocities were used to determine Reynolds number, and those Reynolds numbers were then used to determine the corresponding velocities that would be used during the water tunnel tests, so that we can compare our water tunnel tests with our non-fire and live fire tests. So once we had determined our water tunnel testing velocities, we were able to begin our CFD analyses. We performed two-dimensional CFD analyses using the fluid flow analysis system in the ANSYS Workbench program. These analyses first simulated our water tunnel tests that we will do next semester, and those simulations allowed us to obtain theoretical flow around our flame holder design for both configuration 1 here and configuration 2 here. So here are the results from our CFD tests. On the left, you can see configuration 1 and configuration 2 when testing at the minimum flame holder assembly inlet velocity for the water tunnel tests. And on the right side, you can see the same configurations while testing at the maximum flame holder assembly inlet velocity. If you notice, the flame holders in configuration 1 have mirroring recirculation zones, which are shown by the low velocity blue shaded areas here. However, when we offset the top flame holder, the recirculation zone of the bottom flame holder greatly decreases in height. Therefore, this supports our prediction that the coefficient due to drag will decrease when we offset the flame holders. After we completed our water test simulations, we moved on to our non-fire test simulations. These gave us theoretical drag coefficient values, which also confirmed that when we move our flame holders from configuration 1 to configuration 2, the drag coefficient will decrease. This graph, or this table, shows the changes from configuration 1 to configuration 2 based on all of our testing velocities for our non-fire tests. All right, so moving on to next semester's tests. Before we do our water tunnel tests, we must 3D print the models that we will be using for them. We will print 2 flame holder models scaled up to match our blockage ratio that we will be using in our non-fire and live fire tests, since the water tunnel has different dimensions than our afterburner. So when we do our water tunnel tests, we will use the same configurations that have been shown previously, and we will implement a testing method known as particle image velocimetry, or PIV. PIV uses particles injected into the flow to visualize the flow of the liquid or fluid moving through your test compartment. This will give us physical flow visualization to confirm whether or not our flame holder design creates recirculation zones, and will also help us see if our afterburner will function properly. Next, we will move on to our non-fire tests after water tunnel tests. We will create models of our flame holders and of the shell of the flame holder assembly to use in a full-scale model of our afterburner assembly itself during these during these tests, since our actual afterburner may not be fabricated quite yet. So during our non-fire tests, we will test for how changing the position of the flame holders affects the drag on the outside faces of our flame holders themselves. We will test them in the same 2 configurations as shown, and we will get our measurements using strain gauges along the faces of the flame holders, using a basic force balance mechanism. The final types of tests we will perform next semester are our live fire tests. We will do a total of 12 tests, 6 for each configuration, and each test will test at a different, one of the predetermined velocities that we came up with. The first test will start at the lowest velocity and lowest air-to-fuel ratio, and in that test we will increase the air-to-fuel ratio until we meet our maximum. Then in the next test we will move on to the second velocity and so on after that. And these tests will help us determine how the position of the flame holder affects the blockage ratio and the flame stability within our afterburner. I will now hand it off to Karina Lyon to talk about instrumentation.
The instrumentation is important for us so that we can measure the relationship between moving the location of the top flame holder in the horizontal direction, and see how that affects the parameters such as velocity, pressure, temperature, and coefficient and force due to drag. To measure those, parameters, we'll be using type J and K thermocouples, pressure transducers, pitot tubes, water-cooled pitot tube, a rotometer, and strain gauges. The image right here shows our current instrumentation plan. It is important to note that the rotometer is not on this instrumentation plan, as it will not be actually attached to the afterburner. It'll be on the fuel line. Also important to note is the strain gauges, these right here, will only be used in the non-fire test, whereas all the rest of the instrumentation will be used in the live fire test. We will be using type J thermocouples from the inlet to just before the flame holders. These type J thermocouples are very accurate at the temperatures that we'll be measuring at, approximately 560 to 950 degrees Rankine. And then after that, from the flame holder section forward, we'll be using type K thermocouples, as we are expecting temperatures from about 1150 to 1350 degrees Rankine, which is a higher temperature range than we should be using type J thermocouples. So we'll search type K thermocouples because they have higher durability and survivability at those temperatures. We will be using two different types of pressure transducers for our tests. We'll be using absolute pressure transducers and differential pressure transducers. The absolute pressure transducers can measure from 0 to 30 psi, and they operate on a 0 to 5 volt scale. We are expecting to measure pressures from about 0 to 15 psi, which means that these pressure transducers will meet our needs. For the differential pressure transducers, they measure from 0 to 15 psi and operate on a 0 to 5 volt scale. We're only expecting to measure about 1 to 3 psi in differential, so these have a very good range for what we'll be using them for. Then to measure the velocity, we will be using pitot tubes, and this is where we will be implementing the differential pressure transducers. The pitot tubes will take a differential pressure measurement, and from there we will calculate the velocity from that, the difference between the static and total pressures. We'll also be using a rotometer. The current rotometer that we have is calibrated for propane at 40 psig, and it can measure from 0.0033 to 0.025 pounds mass per second. If we decide that we need to add it or remove flow propane, we can change out the float to a float of a different density so that it can measure a different range. This next section, I'll be talking about some of the testing safety procedures and considerations that we've taken. Right here we have the basic layout of the propulsion lab. Right here is where we will be setting up our test stand. We'll have our computer station right here where we'll be taking all of our measurements. We also have marked on this the primary, secondary, and tertiary routes that we will be using to leave the lab in case of any issues that we have with the afterburner. Right here we have a more detailed layout of our test stand. Right here and right here we have two different safety shields that we'll be using. The one right here, it goes around the afterburner just before the flame holders, and then we have this one that will be set around where we will be taking our measurements. In addition to the safety considerations that I just mentioned, we also made our design aware of the fact that we were going to have high temperatures, and we want to make sure that we're not going to destroy our components during one test. So we did a temperature factor of safety analysis, and as you can see from the table right here, all of our factors of safety are greater than 1, which indicates that our components should survive the testing conditions. In this next section, I will explain the budget that the team has and how we'll be using it. So for the course of these 2 semesters, we have a budget of $800. Currently, we are estimating that we're going to use $481, which means we have $319 left over to use in case of anything that comes up later in the semester, anything that we haven't accounted for in our current cost analysis. This shows the itemized budget. Currently, our largest expense is going to be the sheet metal that we're going to be using for all the casing components and the flame holder assemblies. So currently that's about $260. Then we're also going to be purchasing fasteners such as nuts, bolts, and washers, and the cyanoacrylate glue. And we're also going to be purchasing a fuel injector, flow valve, and an igniter and propane to actually run the tests. We'll now hand it over to Catherine to talk about labor hours.
Over the course of the semester, our team has worked 1,158 hours. We were projecting to only work 960 hours. We came up with that number by 12 hours a week, 5 team members times 16 weeks. We did the math and we discovered that we were 17% over on our hours. I attribute this to poor organization on my part as the DTL, not knowing how to organize things and have things due. As you can see on the graph, we were reliably over our hours, so next semester we will be increasing our estimate. Our breakdown of hours by work type, the majority of our hours actually went into general hours, including meeting times, group discussions, group work sessions. The next highest were our professional hours, including report writing, presentation preparation. After that, we have the majority going into research because we did not have a huge amount of background on this topic, so we had to look into it a lot to find what all it was that we would need to do over the course of the semester. In conclusion, we will be making a multiple configuration afterburner with a square cross-sectional area after the inlet with a blockage ratio of 0.375. The flame holders will be connected using plates and then inserted through the sides of the flame holder assembly. Our air source will be an electric blower and our fuel source will be propane. Looking forward to next semester, we will begin testing in the water tunnel immediately. After that, we will conduct our non-fire testing and then evaluate our design based on the results and analysis that we obtain from those 2 tests. Depending on the results of this evaluation, we will either have a short redesign period or begin immediately building the afterburner. Then we will test the effects of moving the top flame holder in the horizontal position and then come up with an analysis of these effects. Does anybody have any questions?
Sure, we can get started. So a couple presentation type things. There were a lot of opportunities on a lot of these slides to include pictures. Like the first one's at slide 5, for instance. You're talking about like a blower and you're describing a lot of great stuff. It would be really helpful to include some photos of what those assemblies looks like or what the kind of product is that's being included. Also, when you're talking about requirements, there's a lot of like, we also want to do this, we also want to do that. Requirements tend to be a little more definitive on this is what we're going to do and maybe this is how we're going to go about doing it this way. It just seemed like a little loose language there that I would like to see cleaned up. I'm not familiar with ASA plastic. What method of 3D printing is used to produce that? And what is its temperature limits? Does it look like it had the smallest factor of safety about everything?
I'll pass it off to Justin, our materials expert.
Matthew knows a little bit more about that, so we'll pass it to him.
Okay, so ASA plastic actually does not have a super high melting temperature. Is that kind of what you were?
Sure. So,
but part of why we're using it is because of the geometry of the shape. So, and it be taking the brunt of the actual temperature. Most of that should be towards the back in the flame holder assembly and the heat chamber. But if you want an actual value, the real melting temperature of ASA plastic is around 280 degrees Fahrenheit, so nowhere near the temperatures we will be getting up to later in the assembly, but I don't think it will affect it by that much.
Okay. What I guess is driving that, I mean, I'm looking at factors of safety that have like a 1.1 for temperature as far as that goes. How confident are you in your thermal analysis to say that, you know, we're sure that we're 1.1 safe, we're going to be fine, you know, or is there some conservatism built into the analysis? What is making me have a warm fuzzy feeling that it's not going to get too hot?
I didn't do those calculations, so I'll do that.
With that, that is an overestimation of our current calculations. Our current calculations don't take in radioactivity, so we increased our calculation. That is not a calculation that is finished yet due to the constraints of time this semester. So we increased the amount of temperature we're expecting to see in that. In addition to, Catherine, do you mind going to about slide 80? Down a little bit more. Right there, 85. In addition to that, we have researched into an insulation piece that if need be, we do have a piece set aside in case future calculations show that it can't withstand that, to help resist all of the conduction temperatures that we'll be getting to that piece, as well as we're looking into any way to stop that radiation with the type of covering at this point in time. We don't have that done.
Okay, cool. Yeah, that's something to look at. Just, you know, whenever you're putting up numbers that say that we're going to be really close to our margin, the way you allow things close to a margin is you say our analysis, we're pretty confident in. So include that as well. In the all-up assembly, you talked about how you're manufacturing engineer, how you're going to be making a lot of these pieces with the sheet metal, and there's little tabs that are connecting each of these segments together. How are those tabs manufactured into your sheet metal assembly? How are you plumbing it?
Currently, we're looking at taking some of the extra pieces cut off from the remaining of the stock, and then either welding those together, or finding a thicker piece of stock to create whichever is more reliant. That is not a guaranteed piece right this second. It is something we're currently looking into that we have multiple possibilities for.
And my last really quick question was, how are you mounting the flame holders?
We are going to be welding the flame holders to the end plates, and then there's going to be a ledge that we can slide them through and rest them on the outsides of the assembly itself, and then we will be taking them in using HVAC tape.
Okay, cool. It would have been really great to talk a little bit about that this is the process. Thank you.
Okay. I got a few. So, starting at about slide 5. So, the Toro Power Jet S100. So that's leak blower, right? So, what from my experience with leak blowers, they don't. You have specific test conditions you want to achieve, but it's basically just a knob. How are you gonna? What kind of speed control are you using for? Are you just measuring what it can do and correlating that speed to a setting, or?
Yes, that's what we were intending to do next semester.
Okay. So that kind of answers my question on your test conditions. What else do I have? So how long when you do your live fire tests, how long are you going to be running it for?
30 seconds.
Okay.
go through a little bit of my process. Initially, I wanted to test for drag forces in the wind tunnels on campus, but I wasn't able to get permission to use them, plus with the multiple flame holders in there, I wasn't quite sure how we would actually set it up within the wind tunnel, since it's usually just for a single product test. So, and that was about half of the semester. So then, once we decided, we're not going to do wind tunnel testing anymore, I kind of decided and was recommended to go towards something like this. There will be calibration tests that will occur, and I think if we go up one slide, so the flame holders themselves won't be connected to the sides of the walls, they'll just be very close, and they'll be mounted to stings so that they can move. And we'll do a calibration test based on that. But this is just based off of kind of minimal research that I've done, and I didn't want to overextend and start saying things that I didn't quite understand yet. So.
Okay. So basically, you're going to use a caliper for each of the strain gauges and kind of like a skin balance or something like that. So you know the force, and then you're just measuring the strain, and then you just use the caliper.
Yes.
Okay. Thanks. Good job, guys. Thanks.
So with a leaf blower, I'm imagining it's a very a lot of rotation in the flow. Is there any intent to flow straighteners instead of your engine?
We were looking at placing honeycomb in the beginning, but we have not had a chance to analyze how the flow will be coming out of the blower yet, so we were holding off on saying that we will be doing that until we have had a chance to do that.
You're gonna need it.
Yeah.
I did a quick Google, but I didn't believe your number on the CTE to 316. I remember numbers were significantly higher than that. You're using a value that at room temperature, the CTE will change the temperatures pretty significantly. It gets quite higher with 316. And which relates to you talked a lot about the CTE, but you didn't say anything about thermal stress analysis, which would be the whole reason you'd be looking at the CTE. Did you do any thermal stress analysis?
We're currently working on that. It's not completed yet, which is why we didn't add it into this presentation. A lot of it is we're worried about the movement and adjustment between different instruments, as well as the piece of glass expanding at a different rate and cracking or having any faults along those lines.
Which is the thermal stress analysis.
Yeah.
And under the transfer analysis, with the point made earlier that there's lots of opportunities for fiction. You've done this heat transfer analysis, especially trying to figure out this heat, right? I would like to see a lot more in the results of what went into that. That you can use your temperature margins of safety to see anything about gas temperatures and what temperatures went into that margin calculation. And the Reynolds number that you calculated, what was your characteristic length?
So, since it's internal flow, I was using the hydraulic diameter of our test compartments. So for the water tunnel, it was a rectangular test compartment, and so I used the bottom equation, and for the actual afterburner itself, it's a square cross section, so I used the top.
Is that a backup slide or was I sleeping somewhere?
That
It's a
was
backup
a
slide.
backup slide.
And so the flame holders themselves are not part of the Reynolds number calculation?
No.
Not sure. With your schedule, you talk about the water tunnel test, and you talk about feeding back results of that. You're
like the intention of your project is to leave this in place and let future classes use it. So I'm wondering what you're going to do for connecting all the electrical parts and documenting them so classes who come in later can use your stuff. Because I didn't see anything in the budget for like jumbo blocks and junction blocks and anything that's kind of what I consider permanent.
So most of the instrumentation that we'll be using on this belongs to the propulsion lab, and they are necessary to use in other classes. So the instrumentation, for the most part, will not be affixed to the Afterburner. We do have to be able to take it off, but we will have a safety and operation manual which will detail how to set up all of the instrumentation.
That's it. Questions?
Slide 22. Okay, the pressures, are those static pressures or total pressures? In that?
I think they're the total pressures when we calculate it.
Okay. So, as a propulsion guy, when you go through a combustor or afterburner, total pressure drops. Luckily, it happens in a combustor, so then you can actually flow air out of the turbine blades. But in this guy, you got pressure increasing, so I've been wrestling with what's going on. One of the things I don't like is that CDB at the very end. If I up the drag coefficient, my pressure gets better. It's a miracle. You should patent it. Okay, so something's not connecting to me. So I don't know what it is. I know it's not my numbers I'm running, but I think I look real careful because when a red flag went off as soon as I saw exit pressure higher than inlet pressure because Mother Nature gets it up. Just be careful. That's all you have.
What's atmospheric pressure? This is 12. What's atmospheric pressure here in Prescott?
It's less than at sea level, so it should be below 1 atmosphere, so I think around 0.95, if I remember correctly.
What? 95%? Is what you're saying?
No, I'm just saying it's less than. I don't remember what the exact atmospheric pressure would be.
It's around 12 psi. Absolutely.
Okay, yes.
Okay. So your assumed inlet pressure is 12.45 psi gauge.
Yes.
So you have a 1 atmosphere pressure source. Is that your leak flow?
That was just using the current conditions for this location.
So that's an absolute value. So you need an A at the end of it.
Yes.
Okay, so that's an absolute value. The average exit pressure is higher than the absolute value. That goes back to Dr. David's question. It's all about minimizing pressure loss. There is no hope of pressure gain in a device like this. So be careful how you look at your analysis. Something not quite right about that. I do have a question on the CFD results. So that's slide number 45. So you were talking about the recirculation zone, and I'm hoping to see is blue negative. How do I know if recirculation is happening?
So, actually, we have a different slide.
Oh, that would be good.
That's a little bit more close to relation.
Oh,
So,
yeah. Oh, my goodness. Oh, I like that slide.
These are, the ones I used in the actual presentation were more to show that it's, the velocities are mirrored in a theoretical situation, whereas these actually kind of show streamlines of what we would expect to see in the water tone test.
Okay. So, with respect to this recirculation zone, it looks like, okay, so comparing the two, it doesn't look symmetric to me. The top one looks symmetric, but the bottom one doesn't.
Oh, yes.
And so does that make sense to you?
Okay, yes, I'll explain. So the top ones, are,
No, on the bottom, excuse me, on the bottom where you've got the offset.
yes,
So the one that's offset back,
yes.
okay, looks really symmetric, and then the one that's this direction, I'm not, it also looks symmetric, but it looks weird.
Yeah.
I would expect the whole thing to kind of shift down. I know you've got a wall on the other side that's kind of preventing that. So I guess I want to, when you look at that, does it make sense?
I think it does, especially with our predictions.
Okay.
It's just the bottom two, where the flame holders are offset, we predicted that the coefficient of drag would decrease, which is, according to our equation, based on the height of the recirculation zone itself. And so it's not really a matter of if it's symmetrical on those ones, because it's supposed to be symmetrical when the flame holders are directly above each other, but not when they're offset. And when they're offset, the bottom flame holder has a much smaller recirculation zone height corresponding to the decrease in coefficient of drag, which makes sense to that would happen according to what we predicted. So
Okay, so that's what you expected to happen.
that's what I guess. That's what I said.
Oh, just on your slides, trying to connect, just go ahead and give an example. So slide 38. You've got different colors, different shapes, and I kept having to go back to your overall drawing to find out what that meant, what the orientation was. Sometimes I don't know if the flow is going this way, if the flow is going this way, not going anywhere. So help yourself out. If you got just a small little rendition of your initial CATIA drawing, it shows the different pieces, and it looks like you're trying to color code them. So that when you're talking about it, is that just colored to make them different, or is that colored to identify different materials? So really hard when you had the slots, and I saw these two windows, and then I'm like, okay, those are the slots. Which direction are we looking at? So it's difficult from the viewer standpoint to put that into context. Okay, I know you give the dimensions, but there are two 8-inch dimensions. You've got the 10-inch, and I don't remember that from where we saw them before. So it would really help to do that, so we can find out what the perspective is and where that is in your terrain, especially for temperatures. And then you talked about what materials you're using. So that's probably a kind of a wasted slide there. You've got a dimension, you have a dimension. If this is your heat chamber, give me some properties of your heat chamber. Give me where it is, and you probably might not need the next slide. Give me everything in one piece. I'm still confused on slide 7. You've got your analysis of effects on blockage ratio, on drag, on blow up time, on flame stability. So are you changing the blockage ratio?
Not per the geometry. So the geometry of the flame holders and the channel will also be the same. However, that's where the predictions come in, because as you shift the top flame holder, the distance between the two flame holders become greater, allowing for more flow. So if you were to do an analysis on each flame holder themselves, no matter where it was positioned, the technically block ratio would stay the same. But over the whole system, the blockage ratio and drag coefficient for our prediction should decrease due to that increased area between the two flame holders.
Okay, so the blockage ratio is a geometry consideration. how are you gonna calculate the effective blockage ratio? That, and I would assume that's what you're looking at, is even though the technical term for blockage ratio is the same based on the geometry, the effective blockage ratio is gonna be different. Is that correct?
Yes.
And how are you gonna determine that?
I think for the drag coefficient, that too will come into play, just from our non-fire test, because we'll have the forces. And then we were ultimately looking at the condition. So, unless I'm incorrect if I'm wrong, we didn't have a direct way of measuring the blockage ratio. We had a direct way of measuring the change in velocity by altering the front roll position.
Okay. And then go back to your blockage ratio equation to say, look, this is what the blockage ratio is
Exactly.
for what this is.
Because we'll have changes in pressure and
Yeah,
density.
kind of confusing, so I'm thinking blockage ratio is what you set, what we designed to, and then drag you measure, blow up time you measure, time stability you observe. Okay? So it looked like apples and oranges with this analysis effects on, so make sure that when you talk about calculating blockage ratio or calculating something, that you're consistent with what it is you're doing from an effect standpoint. Good job.
You're going to be. I've worked with Green in the past. I myself am pretty much, call it like a program management side, company owner type. I'll just have like some basic comments of what you guys delivered. I thought that was pretty cool, and I did get a nice top level of what an afterburner is and how it works, which I thought was really neat. But there were just some minor things that bugged me a little. One was, when you put, let's say the ground stuff, when you're talking about, let's say the material, the glass, you were saying, here's a softening temperature, here's a bonding temperature stuff. Right next to it is, but here's where we're operating. That way it gives us the warm feeling right there. I mean, that way it gives us a justification why you selected it. That way it also gives us an idea of what the margin would be. Give us a warm, fuzzy feeling, so there's no questions on that. On slide 31, you're talking about steel and glass. I was told that there's like 4 times delta thermal expansion. That's huge. But there was no mention as to, how you can address it or anything like that. Because glass is obviously very prevalent. And if it gets stretched, now you're talking about how you're going to hold that in. It's going to flow, what it does, you're going to have leakage, etc. Things you got to worry about, right? And then the strain gauge one that was already asked, I still don't understand it, but it was asked, and you guys answered it. I would recommend, you do the thermal analysis of the assembly so you know, because the part is, what is the whatever plastic it is. Still not clear on the heat transfer path. You did say you might put some kind of ceramic there to, I don't want to use the term shield, but as a blocker or a thermal resistor, if you will, right? That would probably help. But yeah, there's nothing clear there. All I have is plastic going to metal, conduction, and I see it melting. And then on the itemized thing, I know the university pays for stuff, but you can't say something is 0 even if it is. You can't, because I remember I once nailed some guys over at ASU, because I do this over at ASU as well. And I was looking at, these kids had done it in the Commons Diego. And I saw it, and then they showed me all this really cool stuff that they had done. They welded it themselves and all. They told me that they bought the material at a salvage yard and all that. And I noticed that I would say the suspension was made out of 6061 aluminum block. And it had been machined, 6-axis machined. And I asked the guys, hey, so what was the total cost? They said, well, it only cost me this much. And I said, well, you got some really high-end material stuff here. Oh yeah, that one, Jim's dad owned the shop, and he gave us the thing. I go, so where'd you get 6-axis milling? He goes, over here at ASU. I'm like, those machines cost X amount per hour to run. The only reason I'm saying it is, as a person who hires people and builds stuff, nothing is free. So at the end of the day, it's just put it on there, but you can say, hey, you know what? It doesn't count against your budget. But you have to understand that stuff costs no matter what. It just does. And when we have government funding and limited budget, we got to watch all that. And little things like machining and all that kind of stuff, you have to understand it at least get a rudimentary understanding of it. And Karina knows, we were running some tests over here. Professor Zwick tried to get it for next to nothing.